Hey guys, this is Mr. Gloy again. Hey, we're dealing with this acceleration packet. We did the first couple pages yesterday, and we're going to maybe do another few more pages today. And what we talked about really was what acceleration is. Acceleration is just a word. It's a word means that the object's getting faster or it could be getting slower. Um, Now, there's also some acceleration when we turn a car. We're going to deal with that another time. In this packet, we're just looking at objects getting faster. Now, we started with a VT graph, and we had this car go from 10 to 20 to 30 to 40 to 50. In this case, it was meters per second. It could be miles per hour, but the velocity is changing then 10 units of velocity every second. So we got a slope of 10. And kids, that's what the acceleration really is. It's the slope of a VT graph. And we were able then to come up with this how fast equation. This how fast equation then is VF equals VI plus AT. You know, we didn't need this equation when we were dealing with constant velocity, did we? Because the object stayed at one speed. But now we have to have an equation, or we have an equation that can help us determine the speed when that speed is changing. What we have is VI, that's the initial velocity. We have A, that's the acceleration. We have T for time. We can multiply A and T and then add it to any VI that we have, and we can get then the final velocity of the object. So we then talked about what an acceleration time graph is. That's a horizontal line when an object's constantly accelerating. For this car, it was 10, right? So we drew a horizontal line here. And now then we need to get the displacement time graph, or the position time graph. Well, we did that by taking areas. We took areas, and we were able to figure out that the shape of this position time graph for an object getting faster represents this top opening parabola. All right, and so this top opening parabola then is constructed by taking then triangles 1/2 BH. But we said that there was kind of an equation kind of for that, and it's kind of our how far equation, 1/2 AT squared. So that's kind of where we're starting out with now. We're on page 3, and I'm going to go now to Word, and I'm going to get a pen here. So 1/2 AT squared represents then delta x, or how far. Delta x then is xf minus xi. That's called then our displacement. Now I've got to tell you that this is just part of the formula. On page 4, I'm going to complete this formula because there's really a term that we haven't added in yet. So this is really just kind of part of this how far equation. We're going to complete it here a little bit later. But I want to first talk a little bit about instantaneous velocity versus average. So if you're in your car and you're looking at the speedometer, that speedometer is changing, you can look at that speedometer at any given instant and it can tell you how fast you're going. That's instantaneous velocity. But we also have an idea called average velocity. So you might say, well, I drove to Kansas City. You know, at one instant I was going 30 miles an hour, then maybe 40 or 50 or 60 or 70. You know, every instant you might change. Well, but you can still get what's called an average velocity. Well, let me show you what these are really in terms of a graph. There's our position time graph, right? And so we said then that the car moved, 5 meters in the first second. Then it moved 20 meters. Then 45, 80, and then finally it got up to 125. So in 5 seconds, let me maybe change my colors here. So in 5 seconds, the car made it to 125 then meters, or you could think of it as miles. That's the end point, right? Well, what we could do is we can take this parabola and we can draw then what are called tangent lines. Tangent lines, all they are small lines that follow the curvature of a shape. In this case, it's a parabola. Well, it turns out the slope of the tangent lines tell us then instantaneous velocity. At this 0, our slope then, it's a horizontal line, so our slope is 0. The speed of the car is 0 right at the beginning, right? It wasn't moving. Then our velocity grows. I'm just going to show this symbolically with these V's. These V's grow. Look, the inclination of these tangent lines grow. Okay, now, let me change colors again here. Let me do maybe a different color here. Blue maybe. Now, what we can also do, then is we can take this endpoint and this endpoint, and what we can do then is connect then these two endpoints with a line. Now, that line we can find the slope of. And look, it's pretty easy to do. Okay, we have 125 minus 0 over 5 minus 0. So that's 25 then miles per hour, in this case meters per second. Well, whenever we take then two endpoints on a position time graph and get the slope, that would be then our average velocity, and that's given the symbol V bar, or our average velocity. All right. Now, so was the car going at that average speed? Well, only for an instant, right? So if we draw the tangent line that's parallel to that line, that would represent then the time that it's going the average speed, right? So we know that's got to be 2.5, right? Because the car went for 5 seconds, that's the midpoint. Okay? So for times, let me change colors here. For times less than 250, 2.5. For times less than 2.5, that'd be like down in this region, the velocity is less. The velocity of the car is less than the average velocity of 25, right? Okay? It's getting faster and faster. Then it hits 25. For the times greater than 2.5, the car's speed is greater than the average. Okay, does that kind of make sense? I hope so. Well, let's scroll down. We just got a little bit more to do on page 3 here. Well, let's talk about our motion map. You know, we said if an object's traveling at a constant speed, there'd be then a motion map that would represent constant displacement, right? These are, again, called timing dots. But now things are much different. So this is our t equals 0 point. Remember, these are timing points. Where's the car? At 0, right? At 0 meters. Then 1 second, we're at 5. 2 seconds, we're at 20. Then 45, then 80, and then finally 125. All right? This is our 5th second. Now look at the spacing. The spacing increases for an object that's getting faster. Isn't that pretty interesting? And isn't that kind of the case? So you're traveling further and further every successive time interval, right? That's kind of what it means to get faster. Your speed's going up at a constant rate, but your displacement is changing. Your displacement's changing 1/2 a t squared. It's based on the square of that time. So my spacing's increasing. Well, that ends page 3.